So, with this we have seen that with integral controller actually your frequency deviation that delta f s s is 0, right. So, whatever we have seen with integral controller. Now, next we will come to the what you call that that steady state value for that your generation, right. So, now from equation A I have given some number equation A B, right. From equation A I mean this equation I mean this is actually equation A, this is equation A. I have given this number as A instead of any other thing I have put it. So, from this equation only right. So, delta F can be written as this minus K P into delta P D into R into 1 plus S T G into 1 plus S T T into 1 plus S T R divided by S R into 1 plus S T P into 1 plus S T G into 1 plus S T T into 1 plus S T R plus, this is a plus side here, plus K P into R K I plus S into 1 plus S K R T R. So, this is equation B, this is we are getting from equation A. Now, from figure 14a, that means from this figure, right, from this figure, just hold on, from this figure, from this is actually 14a, figure 14a, from this figure that u is equal to, if you look into that, u is equal to minus k I upon s into delta f, u is equal to, right, minus k I upon s into delta f. That means, from this is u is equal to minus k I s upon s into delta f, that is s into u is equal to minus k I into delta f. So, that means s into u is equal to your minus k I into delta f, and this delta f you substitute here, delta f. If you substitute delta f, you will find that s, it is minus minus plus, and s u will be is equal to, and for your steady state error for u, it is limit s tends to 0, s u, right, is equal to, here you put your what you call that s tends to 0, basically you will get k I k p delta p d r at your denominator k I k p into r, k I will be cancelled, k p will be cancelled, r will be cancelled, is equal to delta p d, because here you put s is equal to 0. So, all these 3 terms will be 1 1 1, here if you put s is equal to 0. So, first term is 0, and second term if you put s is equal to 0, it will be k p r k I. So, k p r into k I. So, we are writing k p r into k I, and here if you put all s, this will be 1, this term will be 1, this term will be 1, and it will be k p k I delta p d into r. So, ultimately 3 terms will be cancelled. So, at steady state you will get that value of this thing, or what you call is equal to delta p d. That means at steady state value of u will become value of the step disturbance, right, or whatever it is. That means, it is whatever I mean philosophically whatever load demand has increased, right. In this case, say it is increased case, increase or decrease does not matter, suppose it has increased, right. That means, if it is a steam turbine, right, it is a steam turbine. So, that equivalent amount of steam will be going as an input to the turbine, such that at steady state that your what you call in per unit value, that it will match to that your what you call the power generation value, right. I mean rather increase load demand value. So, whatever power will generate, that delta P g will become delta P L. So, that is why at steady state whatever value will be, that is equal to actually will become delta P g s. That is why that u steady state value we have taken like this. So, from your assignment or numerical problem, without looking into your what you call, without looking into data or everything, you must know that suppose suppose it is suppose delta load demand has increased to your 1 megawatt, right. Then what will be the steady state value of USS? So, USS also will be 1 megawatt, right. So, this should be something like this. That is why I told you, even if you take a proportional integral controller, you will get the delta P d value also. Even if you take PID controller, again USS will become delta PD also, right. So, whether it is PI, your ID or PD, I mean all sort of combination whatever you take, except proportional, right. Proportional cannot eliminate the steady state error, right, except proportional. If integral action is there, right, if integral action is there, then it will be steady state will be your load disturbance, right. It may be combination of integral and derivative, it may be combination of PID, it may be only integral, right. So, those things case it will be PD, but if you take PD or only proportional something like this or only derivative something like this, it will never be like that. It will show some other your what you call USS may become your load disturbance, but generation you will find frequency will show steady state error, right, frequency will show steady state error. So, those things, but in that case if you use PI or integral derivative or your proportional integral controller, you will find frequency will become 0, but if integrator is not there, those frequency will not be 0, steady state value it will show, but at steady state if you check for all these PI, PID, all these things, right, in this case both cannot be made your what you call reach to steady state value. USS steady state may be delta PD may be achieved with proportional or PD or everything, but frequency will never be come to, deviation will never come to 0, right. So, this is one thing, and from figure 14 again we know that delta balance is delta PG minus delta, this is known to you, delta PG minus delta, this is 14a, figure 14a, delta PG minus delta PL into Kp upon 1 plus STP is equal to delta F, right. So, here it is also delta F, this one we are writing, and delta, it is a step disturbance. So, delta PL is equal to delta PD upon S, say. So, delta PG minus delta PD upon S into Kp upon 1 plus STP is equal to delta F, or S delta PG minus delta PG is equal to your S delta F, right, into your 1 plus, just multiply cross multiplication 1 plus STP upon Kp. Now, steady state value for delta PG SS is equal to limit S tends to 0 S into delta PG. Look, every time in bracket S I am not putting, it is understandable, right. So many places if I try to put S things become clumsy, but it is understandable to you that it is all, it is a Laplace function, your function of S, right. So, delta PG SS will be limit S tends to 0 S into delta PG. So, that means your what you call, that means this one if it is limit S tends to 0, if you take this side will become 0, both side you take limit S tends to 0. So, this will become delta PGSS, this will become minus delta PD is equal to this S into delta F, this thing if you put like this, that S into delta S tends to 0 means this term will be your 1, Kp will be there, and we have seen that S into delta F limit S tends to 0 delta FSS, and delta FSS is equal to 0 we have taken, right. That means this will become actually delta PGSS minus delta PD is equal to 0. That means steady state delta PGSS will be delta PD, right. So, this is the I mean if you have anything, just let me write one line for you. This equation we are writing actually S delta PG minus delta PD, right, is equal to S delta F, right, into 1 plus STP upon Kp. So, both side you take limit S tends to 0. So, this is S delta PG minus delta PD is equal to limit S tends to 0, this is S delta delta F, right, into your limit S tends to 0 1 plus STP divided by Kp. So, this is limit S tends to 0 S delta PG is, this one is delta PGSS, this one will remain as delta PD is equal to, this is your delta FSS divided by Kp, right, because it is tends to 0. So, it is Kp, but this one delta FSS we have seen that 0 by Kp is equal to 0, right. That is why delta PGSS minus delta PD is equal to 0. So, that is why your delta PGSS is equal to delta PD. So, steady state here no question of, even if your D term is there, but when you put the controller, steady state value will be exactly equal to the load disturbance. Suppose 0.01 per unit to load disturbance. So, a steady state delta PGSS will be equal to delta PD, right. Now, if you suppose with that integral controller some gain Ki, I will show you some pattern of response, right. If you plot this, so there will be no steady state error, right. This is the frequency deviation. So, it will after some transient oscillation, it will settle to your deviation will settle to 0, right. So, black one is non-reheat, and for reheat type it is slightly peak is slightly higher and slower because of the reheat time constant is there. Here also black one is the non-reheat type, and this one is your red one is the reheat type, right. So, this is dynamic responses with integral contour. This is generation, this is delta PD is the step load disturbance, and black one is the non-reheat type and red one is the reheat type. Ultimately, it is settling to your generation, but this will go to positive, because if of course this is taken as a load increase. If load increases, only frequency will go swing to the negative side, right, then it will oscillate, right. And this is your delta Pg and your per unit megawatt. This is time and this is u, sorry, this is delta Pg and this is u. Plot will be more or less pattern will remain same for you. U also will reach to the your what you call the generation. This is delta Pg, both are same. U also will reach to this same your what you call that same steady state value. I told you that steady state value of u. So, u should match to the generation what you call the steady state value of the generation, right. So, characteristic more or less this one more or less I mean steady state value they are same, and more or less after some swinging it will be there, right. So, dynamic then and if it is if load decreases, say, that means it is going to the negative side, I mean load decreases, then this frequency actually will start swinging from the positive side, and generation will settle to the negative side. That means meaning is generation decreases, u also will be like this. So, in that case, if you take the image of this one, so response will be something like this, right. So, this is your for load increase, this response is for the load increase. Dynamic response is integral controller, but this response is for the increase of the load, right. Load has increased, that is why frequency is initially going to the negative side. Now, if you take that single area your non-reheat type, right, this is a non-reheat type. So, in that case your 1 plus skr upon 1 plus str term will not be there, those term will not be there. So, in that case it will be your what you call, this will be your simple 3 state variables. One is this is x1, this is x2, this is x3, this is your u, and this is your delta f is coming here. That means your here it is delta f is equal to your x1, right, this state variable. So, this is figure 14c. So, with this I have showed you how to write down the state variable equation x1 dot, x2 dot, x3 dot, how you can write, right. So, just for the previous thing I have shown you how to make this state your what you call x dot is equal to x plus bu plus gamma p form. So, if you write x1 dot, here no derivative term is there. So, equations are straightforward, right. So, if you can easily write this state variable equation. So, before your what you call, after that will come composite frequency response characteristic, but before this one more thing I will tell you, but you should know this, that one more thing, that is I will make it here for you, that is actually called that your degree of stability, right. We call degree of stability, right. We define this as I say it is rho. So, what we can do is that we know the equation that x dot is equal to ax plus bu plus gamma p, this we know. Now, look at this diagram, right, look at this diagram, this non-reheat type diagram. Only we will take this one, then it will be easier for you to understand this, right. Take suppose this diagram we will take, right, this diagram we will take. So, in this case for your what you call for a control mode, I will draw this diagram for you. For example, this is your, just try to understand, this is your 1 upon 1 plus STG, this is your 1 upon 1 plus STT, this is your minus delta PL the load, this is your Kp upon 1 plus STP, this is your delta F, right, and this is your delta Pg, and this is your delta E, right, and here your then this is your minus thing is there, this is 1 upon R, and it is coming from here, and suppose you have a integral controller here minus Ki upon S, and this is the thing, right, and this is plus. So, this is minus K I upon S, and the input to this is your delta f, we are taking x 1, and here this one we are taking x 2, and here we are taking x 3, and this was actually u, this is u. From this diagram, if we put output of the controller, earlier we have seen that if we put integral controller, u will not take, we will take this is as a state variable, we will take this one as a x 4, right. So, x 1, x 2, x 3, x 4. Now, if I take non-read type, it will be one more equation, that is x 5 will come, right, but in this case it will be suppose your x 4. So, these are the equation, this is x 1, x 2, x 3, x 4, and that means input to this is here also x 1, and here also it is input to this, here also it is x 1. Now, what we will do, we will write down the state variable equation x 1, x 2, x 3, x 4, but what I will show you that what is degree of stability, you will find things are very interesting. In this case, x 1 is equal to, from this block diagram here, you can write your, this is x 2 minus delta P L into K P upon 1 plus S T P, right. So, go for cross multiplication. If you do, it will be x 1, and I told you S into x 1 means it will become x 1 dot into T P is equal to K P into x 2 minus K P into delta P L. That means, your x 1 dot, right, T P is equal to minus x 1 plus K P x 2 minus K P into delta P L, right. That means this equation you can write x 1 dot is equal to minus 1 upon T P plus K P upon T P x 2 minus K P upon T P delta P L. Say this is, I am marking as equation, because several times we are using a small a, equation A. So, this is first equation for x 1 dot. Similarly, when we will come to x 2 is equal to x 3 into 1 upon 1 plus S T T. So, x 2 is equal to x 3 upon 1 plus S T T, cross multiply, therefore, x 2 S x 2 means x 2 dot T T is equal to x 3. That means, x 2 dot is equal to minus x 2 plus x 3, right, divide, this is your what you call divided by T T divided by T T. So, this is equation your what you call say equation B, that means for this equation x 2 dot is equal to. Next is your x 3 dot, you come to that x 3 will become, that is your x 1 upon R, and this is x 4 state variable is taken. So, x 4 minus x 1 upon R into this one is equal to x 3. That means, if you look into that, x 4 is equal to your what you call x 3 is equal to, from here only x 3 is equal to, this is x 4, we are not taking u, this is x 4 minus, this is minus x 1 upon R. So, it is x 4 minus x 1 upon R, right, into 1 upon 1 plus S T G, right, is equal to your what you call x 3, right, x 3 is equal to this one. So, this is your T G. Now, go cross multiply. So, it will become x 3, then S x 3 is x 3 dot multiplied by T G is equal to minus x 1 upon R plus x 4. So, that means, your x 3 dot T G is equal to your minus x 1 upon R, then this one x 3. So, it is minus x 3 plus x 4. That means, x 3 dot is equal to minus x 1 upon R T G minus 1 upon T G x 3 plus 1 upon T G x 4. This is equation say C. This is your third equation. This is third equation, and this is your second equation. This is second equation, third equation, and one more equation is there, that is your this one, this x 4 is equal to x1 into minus ki upon s. We have taken only integral controller. So, x4 is equal to if you take is equal to your minus ki upon s. That means, your x4 dot sx4 is x4 dot is equal to minus ki. This is say equation D. So, there are 4 equations. So, one by one I will rewrite this equation in one place. So, first is this one x1 dot. So, x1 dot is equal to here I have missed x1, right. Here it is x1, I have missed it, right, because no student sitting in front of you, right. That so if I miss anything, that anyone will correct, because everything I am making it here, right. So, I miss this one, it is minus 1 upon Tp x1. So, x1 dot is equal to minus 1 upon Tp x1 plus Kp upon Tp x2 minus Kp upon Tp delta PL. This is your equation A, rewriting. Similarly, x2 dot is equal to this one, x2 dot is equal to your minus 1 upon Tt x2 plus 1 upon Tt x3. This is equation B, right. Similarly, if you come to equation C, that means this one x3 dot is equal to x3 dot is equal to, right, it is minus 1 upon r Tg x1, then minus 1 upon Tg x3, right, then plus 1 upon Tg x4. This is equation C. And equation last one D, that is x4 dot is equal to your minus your what you call, no, here also I have missed one thing, it is it is x1, right. So, it is actually into x1. So, here also I have missed, look, x4 dot is equal to minus ki into x1. So, x4 dot is equal to minus ki into x1. So, x4 dot is equal to minus ki into x1. This is equation D. So, these are the all 4 equations. Now, in this equation, as u is taken as a x4 state variable, so no u is involved. So, this equation can be made it Ax or in the form of, this equation can be written in the form of x dot is equal to Ax plus gamma p, right, because no u is involved here, right. So, if we make, that means this side left hand side, right, it is x1 dot, x2 dot, x3 dot and x4 dot, right. This one is equal to your this matrix you make minus 1 upon Tp. First you make this one x1, x2, then x3, then x4. So, minus 1 upon Tp x1, then Kp upon Tp x2, other things are not there, 0 0, right, then plus u is not there, gamma p is there, that is your delta PL. So, delta PL is here. So, minus Kp upon Tp, right. Then x2 dot, it is first one is x1 is not there, minus 1 upon Tt, and this one is 1 upon Tt, and this is your 0, because 1 upon Tt x3, 1 upon Tt x3 here, and here x3 dot, first 3 terms is there, fourth term, your first 2 term, second term is not there. So, it is minus 1 upon Rtg, that is x1, 1 upon Rtg x1, 2 is not there. So, 0, minus 1 upon Tg, that is the third term, right, and fourth term is 1 upon Tg4, right, and your fourth equation only first term is there, minus ki, and here all are 0, this is 0, this is 0, here it is this term ki, and all other terms are 0, That means, for this your what you call, for this system, if you take integral controller, so this is the state variable equations. Hope everything is correct. Only couple of places I missed x1, because everything is writing here, and you people are not sitting in front of me. In the class, student always immediately point out that you have missed, but here, but anyway, this equation is a correct one, right. So, this is your A matrix, right, and this is your gamma matrix, and this is your A matrix, right. So, this is your gamma matrix. Now, question is that this stability of this system depends on K I, right. This is all the parameters are known except K I, right. So, in this case what you can do is the degree of stability rho, you will have 4 eigenvalues, because this A matrix order is 4 into 4, the 4 eigenvalues are there, right. It may be, if matrix are symmetric matrix, symmetric and real, that all eigenvalues will be real, right. But in this case matrix is not symmetric matrix, but these elements are real. So, eigenvalues may be complex conjugate, may be real. I also do not know depending on the parameters, but at least 4 eigenvalues will be there, because there are 4 your what you call that your 4 order of the matrix is 4. So, characteristic equation will be your 4th order. That means, this is the matrix, that means if the characteristic equation is like this, if it is like this, right, that means characteristic equations you can write that lambda I minus A, determinant will be there, this equal to this 0. From that you will get all the equation. Actually lambda is like this, but this writer has become my habit, right. So, it is lambda 1, lambda 2, lambda 3 and lambda 4. There are 4 eigenvalues. It may be real, it may be complex conjugate also, pair of complex conjugate also, we do not know, but for the sake of understanding that, first thing is that all these eigenvalues, if it is that real part, will lie on the left half of the S plane. This is your real part, right, and this side this is your real part is sigma, right, or I can pay real part, right, and this side is your imaginary part. So, one side we made sigma, other side you make your what you call omega. I will not put, some other symbol you can put, say this is imaginary part, right, and this is your real part, right. Then is a put sigma omega something, so this is imaginary part. This side this is 0. So, this side for the stability of the system, all these eigenvalues real part must be negative, right. If system is stable, if anyone goes to the right half of the S plane, system is unstable. So, real part of all these eigenvalues has to be, that means for this matrix real part of the all eigenvalues will be your what you call negative. Now, question is that your stability of the system, all the parameters are known, it depends on the integral gain K I value, right. So, what you can do, for example, suppose for the sake of understanding, for some system, suppose it has eigenvalue minus or minus 1, minus 0.25, and say another eigenvalues are there 2 plus minus j 3 minus, right. So, all are minus. So, if you locate these eigenvalues, one is real eigenvalues here. So, you are locating this eigenvalue minus 0.25 very close to the origin, another real one is there somewhere here, it is your minus 1, this is minus 0.25, and others are far away, one will be this side, another will be this side. So, one will be minus 2 minus 3, this is minus 2 minus your j 3, and this will be minus 2 plus j 3, right. So, these are far away. Eigenvalue which is very close to the origin, right, it is more sensitive to the stability for the system, for linear system. So, this is minus 0.25. So, that means for each value of K I, whatever you have got, for each value of K I, what you will do, that you find out that which will be, for you set K I is equal to say 0, then K I is equal to say 0.05, 0.10, like this you go on increasing, and then degree of stability, actually rho can be defined as, right, it is maximum value of real of lambda I that you take. That means, for this previous thing, suppose eigenvalues are like this, a only real part you take, that means this one is equal to maximum of, it is real is coming minus 0.25, then minus 1.0, then another other two real is minus 2, because eigenvalue was minus 2 plus minus j 3. So, minus 2, and maximum this is minus 0.25. That means, which is very close to the origin, this eigenvalue is more sensitive to the system instability, right. That means, for K I is equal to 0, you will get some value and find out the rho value, then increase the value of K I is equal to say 0.05, 0.1, like this. What you will find, this eigenvalue, particularly this eigenvalue which is very close to the origin, it is actually moving in this direction. That means, it is moving away for some value of K I, going suppose K I is going on increasing, up to certain point this value will be shifting from this value from this side to this side, forget about others, just let us observe this shifting. So, for certain values of your what you call ki, after that further increase of ki, again it will start moving toward this side, I mean positive side. So, at certain point the maximum shift will be there, after that again it will try to move to the your this side. That means, if you plot like this, I mean if you plot, suppose this side, suppose if you plot, suppose this is your, suppose rho value, rho will become negative assuming the system is stable here. So, this is 0 and this side is your ki value, you are increasing the ki value, rho will become something like this and finally it will cross like this, right. So, this is actually from this from here to here, for this range of ki system will be stable, and this is that whatever maximum shifting you will get, whatever I am telling, that you are, this is your say ki optimum, this is the optimum value, and from here that as ki is going on increasing, you increase it, this rho will be increasing up to this. After that, if further increase of ki, that rho will be decreasing, that means from there it will shift to this side, after ki is increasing up to this, after that it will move to this. That means this, that means in terms of that eigenvalue analysis, that this is actually that optimum value of ki, but from here to here this is the range for which your system will remain stable. Although response may not be better, with this kind of technique, with this value you will get the best dynamic performance. So, whatever it is, that degree of stability means you have to find out the roots of the characteristic equation, and then you have to take your what you call that rho is equal to max of real lambda I, that is maximum of all the real eigenvalue, real part of the eigenvalues, and here it is minus 0.25 is the maximum, because negative sign is there. So, this is maximum which is very close to the origin, that we will take and we will change the value of ki. So, this value will shift for some value of ki up to certain values of ki. After that further increase, it will not move away, it will go toward this side. So, that is this graph, that up to certain value, suppose this will go, suppose it has come up say minus 0.47 say from minus 0.25, and after that it is going down, and this is the optimum value for which perhaps you will get the better response. But for other techniques are there, further much better response can be obtained in this one, but this is actually called the degree of stability, and this is the range from which your system will remain stable. I mean all eigenvalues will lie on the left half of the S plane. Beyond this value, it is going to positive side, means rho is positive, means the real part of eigenvalue is becoming positive and system will become unstable. I hope you have understood this, and forgive me for making to your what you call writing error, because I am recording here and everything making it from memory. So, something missed. So, but anyway everything is corrected. So, thank you very much. Thank you.